Thank you for joining us today for our webinar, brought to you by Plastics Decorating Magazine and the SPE Decorating Assembly Division. My name is Jeff Peterson. I'm the publisher of Plastics Decorating and the current chairman of the SPE Decorating Assembly Division. Our speaker today is Scott Sabrine, president and founder of the Sabrine Group. Scott has over 30 years of experience in plastics manufacturing and has published over 150 technical papers. Scott has invented or developed leading-edge processes in laser marking, adhesion bonding, surface pretreatment, product security, digital inkjet, and more, earning over 12 patents for his clients and as a sole inventor in these areas. Scott's presentation today is entitled Understanding the Science Behind Surface Pretreatment for Adhesion to Plastics, Adhesives, Coatings, and Inks. He will provide a better understanding of the science behind surface pretreatment of different plastics and help determine the best solutions to adhesion challenges. Before we begin, a quick reminder that there is a small box on your screen where you can type in questions. If you have any questions during the webinar, please type those in and hit send, and we will address as many as possible at the end of the presentation. So, without any further ado, let me introduce Scott Sabrine.
Thank you very much, Jeff, for the introduction. And I appreciate everyone taking the time today to participate and learn about understanding the science behind surface pretreatments for adhesion to plastics. As Jeff stated, I've dedicated my career, or at least a significant portion of my career, to solving adhesion problems and have had the unique pleasure to consult on site at over 400 factories in 33 countries. Let's face it, adhesion problems are complex issues that extend beyond pretreatment equipment and which model to buy. In fact, when Sabrine clients call us with an adhesion problem, the majority already own the equipment. Maybe it's just not operating correctly, maybe it's the wrong machine, maybe it's the wrong process, but usually it's a combination of all. So let me emphatically state here and now, all adhesion problems are solvable. All adhesion problems are solvable. Some just take a little bit longer than others. On a separate note, let me be absolutely transparent. I'm going to mention third-party companies today, and I want everyone to know I do not receive any finder's fees, remuneration, chocolates, or anything of the like. So let's get started. Plastics adhesion problems are pervasive throughout industry, and there's not a vaccine cure. Regardless of the product your company is bonding, from billion-dollar jet fighters or inkjet printing on logos on a mug, you want it to be done correct the first time. This presentation is going to teach us about adhesion failures and adhesion problems and failure mechanisms, polymer properties, surface wetting, contact angle, and measurement techniques, various plasma surface pretreatments, case studies, and at the end of the presentation, there'll be a time for questions and answers. We wouldn't be here today if our only problem is bonding to ABS. Adhesion problems, as I stated, are complex. There's usually not a single smoking gun. It's usually a combination of factors. And too often, companies and individuals have too narrow of a focus and looking at the pretreatment only as the solution. In my experience, I've found across industry that the adhesion problems and pretreatment problems have likely been occurring for a very long time. And I hear comments from my clients, well, we've been doing this for 20 years. I've just been hired by the company and I'm taking on the project, so I'm just learning. Everyone's left the company, a combination of all of those. Our project started with polymer A, which was pretty easy to bond, but now we're manufacturing polymers A, B, and C, and we're having all kinds of problems. Our design and manufacturing departments are separate. Sometimes they're in different countries. And don't be too surprised when I tell you that a lot of people have said, oh, I saw this piece of equipment at a trade show. It looked good, so I bought it. Or I bought a lower cost version of it on eBay. So if any of these sound familiar, and I hope that they do, then you're in the right place. My mission today is to provide fresh insights into identifying adhesion problems and integrating best manufacturing processes. So let's get started. Adhesion problems originate from many sources, and we're going to examine all of these today in great detail. But as you can see, the sources, the contributions of the problems can start from design, injection molding, incoming materials, storage, pretreatment, assembly operations, as well as failure modes that happen in the field. So as engineers and scientists, we need to make sure we do our job and eliminate all of these sources of problems. So let's examine and briefly define what kind of failure mechanisms we generally see in industry. And it's very important to understand where the failure mechanism occurs, and that's the first step towards solving a problem. So in the center photo, you can see adhesive failure. That's the most common mechanism that we see. And adhesion failure is when the adhesive bond line separates from the two polymers that it's joining. And these polymers can be like or dissimilar materials. Obviously, we want to achieve a stronger bond, and that would be the cohesive failure on the right. And in this failure mechanism, the adhesive splits within itself, meaning that we have achieved the full strength of the adhesive that we're trying to bond. On the far left is structural failure. It's always great if we could achieve this. This is the highest level of bonding that can be achieved, the optimal bond strength, and this is where the material, the polymer, cracks within itself, indicating that the adhesive bond that we're using is even stronger than the material. And for inks and coatings, we strive to achieve zero removal of the coating, the paint, from the base material, as would be tested by ASTM standards. The theme that we're going to have throughout today's webinar is design for manufacturing. So let's look at some of the reasons why bonds fail. And on the next slide, we're going to extensively detail all the critical control points. So why do bonds fail? The first reason, and in the purple circle, is by the nature of the part design, and that would include the geometry, the adhesive, and even the bonding process. Plasticizers and stabilizers that are in the polymer formula, if any mold release is used during injection molding, storage conditions, and of course, highlighted in red is over or under treatment. The final three indicate, well, if we've done everything right, we still have to design our product to withstand the rigorous demands that are going to happen in the field. And this can be sterilization methods, a very harsh environment in ground or in the ocean, as well as photooxidation. Let's examine the critical control points in significant detail. And there are many categories where we're going to see failure. So as you're designing your processes, pay attention to each of these, and I hope I'm going to bring out some points that otherwise you may not have thought of. So everything begins with the design of the part. Whether you're going to succeed or fail, begin with the product design team or the industrial designer. The selection of polymer and the additives are the first point, and this is where everything in the process is going to trigger upon. The type of colorants that are used can affect the pretreatment, the joint design, texture, and the type of adhesive. So in the design phase, all of this is going to predetermine how effective we are during final assembly. Well, let's look at the factors that can happen during injection molding or primary processing. Drying of the material, particularly when they're hygroscopic and hydrophobic, are very important. During injection molding, how is the material actually packed? Is it a resin-rich surface or not? Whether or not, depending upon how much glass fill is in the material, we always want to be able to strive to have it uniform. During injection molding, is any type of mold release used? Silicone sprays. Even if they're not used on your particular machine, if it's used anywhere in the plant, silicone is very highly migratory and will affect everything. How well is the operator handling the parts at the machine? Are they wearing gloves? And what about the cleanliness of the conveyor? If the machine operator and the conveyors are dirty with grease, then you're going to have cross-contamination. Then let's look at incoming materials. After injection molding, how have the materials been packed? Are they in poly bags? Well, if they're in poly bags, that's probably one of the worst packaging method there is, because the poly bags often contain low molecular weight species that migrate to the surface. So if in fact that's how they're packed, then it's very common for some parts that have been more intimately contact with the packaging are going to be contaminated. Also keep in mind time and temperature, since injection molding or primary molding make a big difference. And when it comes to material storage, temperature, as I've highlighted, is generally more important than humidity. And we'll talk about that in the next step. When we have storage and inventory, how long have the parts been in storage? Again, temperature is a very important factor. Humidity is too, but humidity is going to be more of a factor in pretreatment. So if parts have spent a long time in shipping or in the warehouse, then low molecular weight species are going to migrate to the problem. And if they're packed in poly bags, all of this makes a big difference. So let's assume everything is correct up to this point. Everyone has done their job. Let's look at pretreatments. Before pretreatment, it's imperative to always wear clean parts, always have clean parts and gloves, hand protection. Without question, the plasma method selected makes all the difference in the world. Once the plasma method is chosen and it's the correct one, the single biggest issue we see is undertreatment and overtreatment. In this particular case now, humidity conditions during pretreatment, certainly of atmospheric plasmas, affect the level of pretreatment more than temperature. So keep in mind, humidity has the most effect on the actual pretreatment. Temperature has an effect on the migration. We also want to make sure that we've achieved the proper contact angles and the amount of time until bonding. Now, let's assume all of this is done correctly. We move on to final assembly. Adhesives and coatings, what type of adhesive has been used, or the coating? We have to have the proper mixing and viscosity. The dry film thickness needs to be 100% accurate. If it's too thick, then it's not going to dry or cure correctly. If it's too thin, process inconsistency. And always remember, when you're trying to mate two polymer parts, it's always wise to have clamping during the final assembly process as well as curing. And then, of course, the final step is you want to have great quality control and statistical process control. So when you look at all of this, all of these factors, everything can be perfect. But if you have mistakes in final assembly, it doesn't matter what's happened beforehand. So I hope this opens up some eyes on what to look at in your process. Let's examine polymers. And today we're going to focus on thermoplastics, which are amorphous, which can be either amorphous, semi-crystalline, or a combination of both. So we're going to look at why are plastics difficult to bond, their morphology, properties, thermal properties, and best polymer applications. So why are plastics difficult to bond? And bonding, when in this context, means you're going to be using printing inks to plastic. It can be adhesives and sealants to plastic, paints and coatings to plastic, plastic to plastic, and metals to plating. Why are they so hard? 4 reasons. Polymers are hydrophobic, nonpolar, chemically inert, and low surface energy. And isn't that great for the designers of the product? That's exactly what they wanted to do. They wanted to make the part as resistant to the outside world as they can. However, that's the nemesis for all of us working in manufacturing. So the rest of the presentation is going to be dedicated to how we work around this and solve problems. Let me be perfectly clear here. Polymer selection and morphology matter. While I'm discussing about different polymers, think about the polymers your company is using. Are some of them easier to bond than others? Remember, your design engineer has chosen this polymer, but is it the best selection? So as we look at the pyramid of polymers, performance increases as we get toward the top of the chart. The most difficult materials to bond, obviously, are PPS, PTFE, polyesters, and these are your high temperature plastics with super chemical resistance. They're good for wear resistance. And what we really want to look at here is focus on, in the center of the pyramid, PET. And you can see it's adjacent to nylon and acetal, and look at it in regard to ABS. Anyone can bond ABS, but it's very important to examine which side of the polymer pyramid do we have amorphous or semi-crystalline. The crystalline are highly ordered molecules. The amorphous are random, but also very important to keep in mind that in certain conditions, polymers such as PET, PBT, and common polyesters, as well as nylon, can be they're semi-crystalline and can be either exist in both states. So they can have both amorphous regions and crystalline regions. So when it comes to looking at which are the most difficult polymers to bond, you can see on the semi-crystalline side are your polyolefins, your acetals, your nylon, polyphenylene sulfides. Amorphous tend to be easier to bond to. So it's very important to keep in mind and select polymers and their morphology which best meet the application. So let's see how the implications of this affect us in some of the material properties. The thermal properties are critical to understand and imperative to prevent overtreatment. Remember that most of the pretreatments add heat to the polymer substrate. So as Sabrine is working on different applications and trying to best optimize the pretreatment, what are the parameters we look at? First is the heat deflection temperature. This is the temperature when the material starts to soften when exposed to a fixed load at elevated temperatures. We also look at another property that's on the technical data sheet, and that's referred to as the Vickett softening point. The Vickett softening point is the temperature at which the specimen loses its stability form and begins to soften. One of the things that you'll see is that the Vickett softening point is closer to the polymer melting point. So these are very two important parameters that we're always looking at to make sure we're not getting too close to the melting point of a polymer, because at that point we're going to overtreat. While we're not going to go into the detail of the glass transition temperature, obviously it's very important to know what that value is, and it's the temperature at which a crystalline or semi-crystalline portion of the polymer melts and changes from an ordered structure to an amorphous structure. And keep in mind, as I had stated on the previous page, that materials are not always either semi-crystalline or amorphous. They can have combinations of both of those. So thermal properties affect pretreatment type, the power, the duration, and the speed. So let's really look at what's happening here. If we take an extreme case of nylon, and your design engineer initially says, well, the material we're going to use is nylon 6/6 plus 30% glass. That's the second row that I'm showing. Well, it has a heat deflection temperature at 264 psi of about 250 degrees centigrade, a Vickett softening point of 240 degrees. Let me back up just a moment and tell you that the thermal properties I've stated on this slide are very generic data. Do not take them as absolute, because you can look up in 10 or 20, 30 different tables, and you're going to typically see ranges of temperatures and different temperatures depending upon who the manufacturer is. So emphasizing here just a single value to present general rough orders of magnitude. So we've got 250 degrees centigrade for nylon 6/6, 30% glass. Well, let's say we already have our pretreatment, and now we bring on another product, and this is going to be nylon 6/6. This is the top row. Well, now our heat deflection temperature is 65 degrees centigrade with a Vickett softening point of 90. So if we have that identical process set up, if we have our identical pretreatment process set up, then we have much lower softening points and much lower deflection points, and so that pretreatment is still putting out as much heat, and that's why it's so important that you have to know not only the polymer that you're using, but also what the thermal properties are. Another example of this is that in nylon 11, which is very commonly specified, well, nylon 11 just happens to, well, it is more difficult to bond than nylon 6/6. or nylon 66 plus 30% glass. So and that's due to the longer molecular chains. So if we want to improve our bonding just by changing the material, then we can do that by changing from nylon 11 to nylon 66. But again, we always have to be very cognizant of the polymer properties. And a similar type effect for polyethylenes, whether it's high-density polyethylene, low-density polyethylene, or linear low-density polyethylene, thermal properties matter. So this is one of my favorite slides because I'm going to show you and tell you exactly how Sabrine and our experts go about trying to optimize the adhesion bonding processes for the most challenging materials. I like to call this the 8 or the 10 most wanted list. So when you're operating at this level at the top of the pyramid, I like to think of this that you're landing a jet fighter on an aircraft carrier. And what we need to do is make the landing strip as wide and as long as possible, widen the process window. So there's because there's not going to be much tolerance for air. So in the case of PTFE on the top, PTFE is just PTFE. It's very extremely chemically inert. If your design engineer has chosen that, then you probably don't have any options or don't have much options in terms of the materials. But cold gas plasma is best, and we're going to get to the different plasmas. Acetyl polyoxymethylene. I'm not sure if we have some of our friends from Celanese with us today, but also PO polyoxymethylene is very highly inert. What we have found is that the copolymer Celcon is generally easier to bond than the homopolymer. When it comes to nylon 6, nylon 66, look at the morphology on all of these: semi-crystalline, semi-crystalline, semi-crystalline. So when it comes to nylon 66, it happens to be both hygroscopic and hydrophobic. So for any of you that are experts in this field and you want to say Sabrine is full of it, he doesn't know what he's talking about, because how can a material be both hygroscopic and hydrophobic? Well, one is a bulk material property, meaning that it absorbs moisture. The hydrophobic portion is a surface attribute. So when it comes to nylons, make sure that they are dried extremely well, and keep in mind nylon 6 is easier to bond than nylon 11 or 12 because the molecular chains are shorter. So when your design engineer says to you, oh, we're designing nylon 11 or 12, challenge that if you have to. If maybe it's possible to use nylon 6. PPS, polyphenylene sulfide, also a semi-crystalline, is also very highly chemically inert. What Sabrine has found is that the linear PPS offered by Celanese tends to be easier to bond to and actually have more robust bonds than the branched version. I do believe Celanese probably does offer both versions of this, but linear tends to be easier. Polypropylene. Polypropylene is more difficult to bond than polyethylene. So if an olefin is important for your application, consider polyethylene. Easier to bond because it is more, polyethylene is more thermodynamically stable. I'm mentioning polycarbonate And it really shouldn't be on the top 10 list here because it's not all that difficult to bond. But sometimes companies do have problems with it. It is an amorphous plastic, but it's generally more difficult to bond just because it's hygroscopic and it's very prone to cracking if a strong solvent is used. So I just wanted to briefly mention polycarbonate. Lastly, I'm going to talk about SPS rubber and other types of thermoplastic elastomers, which also are amorphous, but this is one of the biggest breakthrough areas that we're advancing right now. And what we have found is that the type of carbon black that's used in the rubber and the loading level has great significance to the ability for adhesive bonding. We've determined there's a critical threshold level of the letdown and the type. Once one has exceeded that critical threshold, it becomes magnitudes more difficult to bond. So always keep in mind that you want to know as much as possible about your polymers and identify what alternatives there may be. We're going to move on to surface wetting, contact angles, measurement techniques, and different types of analytical testing. Surface wetting. So what is surface wetting? Wetting means that the liquid flows and covers a surface to maximize the contact area and the attractive forces between the adhesive and the adherent bonding surface. For a liquid to effectively wet out a surface, the surface energy of the adhesive must be as low and usually lower than the surface energy of the adherent to be bonded. Alternatively, the surface energy of the substrate must be raised to fulfill the bonding. Jeff Peterson, the host of today's seminar, was kind enough to let me photograph his Ferrari. And so as we were talking about this, I had said to Jeff, you probably don't want to start flame treating your car to help the water bead up. But obviously we know the shutdown and the coronavirus hasn't affected Jeff too much.
Yeah.
So let's quickly look at a hydrophobic, non-wettable surface on the left. And this is a very good representative of a steep contact angle non-wetting. On the right side, I'm going to demonstrate a hydrophilic, highly wettable surface. And this demonstrates the type of surface condition we're looking for to achieve maximum bonding after surface pretreatment. I'll let you look at that for a little bit while I take a sip of water. Moving forward, let's examine contact angles and specifically a static contact angle on the top, on the top diagram. The contact angle formed by the solid surface and the tangent line to the upper surface at the end point is called the contact angle. The bubble or droplet shape is due to the molecular forces by which all liquids, through contraction of the surface, tend to form the contained volume into a shape having the least surface area. Contact angles are generally affected by changes in both surface chemistry and changes in topography. Well, we all know that something static in nature is unusual, and that just like taking physics classes in college and high school, everything is based upon theoretical. We're doing this in a vacuum, or we're doing that in the vacuum. So it's really more important to look at what happens to a contact angle or a fluid in the real world. And this is where thermodynamic, hysteresis, and kinetic effects become important. Well, we want to break out into two vectors. The advancing contact angle is most sensitive to the low energy or unmodified components of the substrate surface, while the receding angle is more sensitive to the high energy oxidized groups introduced by the surface pretreatments. On the other hand, the receding angle is actually measurement most characteristic of the modified components of the surface following the pretreatment as measured in the dyeing solutions. So let's look at surface energy and surface tension. We look at several polymers: polypropylene, polyethylene, polystyrene, and nylon. The general rule of thumb is that optimal wetting is going to occur approximately 8 to 10 dynes higher in surface energy than the liquid tension, and that is generally based, and that needs, and one needs to take into account whether or not this is a what type of solvent is being used, whether it's a UV or waterborne system. So just real quickly, we want to note that the dyne is a unit of force equal to 1 Newton, when 1 Newton is equal to 10 to the 5th dynes. But look carefully at this chart, because when you look at polystyrene at 33 dynes, you may think that and compare that to nylon at 46 dynes, you may be thinking, oh, well, the surface energy of nylon at 46 is higher, so theoretically it should be easier to bond than polystyrene. Well, as we're going to talk, the answer to that is no. But this is a general indication of where we want to be on surface energy relative to surface tension. Now, a very important part to understand is that texture will improve wetting and bond strength. So when you have a part that's smooth, shiny, as molded, that's going to be the most difficult to bond, and many of our parts that are used in industry do that. So keep in mind, whenever you can slightly modify that to a B1, a B2, or a C1 type finish, that will significantly enhance the wettability and the bond strength, because it's going to allow for mechanical bonding. We've placed a lot of emphasis is placed on contact angle and surface energy, but it's important to understand that surface energy does not mean you're going to have strong adhesion. So we're going to look at different ways of testing the surface using contact angle instrumentation as well as dyeing solutions. Well, I know all of you are familiar with the dyeing solutions. I'm not a fan of them, and you're probably not either. And we all know there's a great deal of variability that happens as we try and test this. So when we look at the dyeing solutions, we can use the dyeing pens, and they're generally an indicator, a directional indicator, as well as the solutions of what the surface energy is. But they're highly unreliable, and just by the fact that you have the tips of the pens coming in contact with the materials, contaminates the tip, and that's going to happen regardless of what the manufacturer supplier says. If we're going to use dyeing pens or dyeing solutions, I prefer to use the bottles and a Q-tip. Not a Q-tip, I want to avoid that. I want to use a wooden applicator. Q-tips actually, the tip are too inconsistent, so when you use the wooden applicator stick with the dyeing pens, you're able to achieve a more uniform result. So as we all know, what happens as we use either our dyeing solutions or the dyeing pen? Well, if we start our testing at 30 dynes, indicated at the bottom, at 30 dynes or 32 dynes or 34 dynes, 36, it looks like we're wetting. We test the 38 and it doesn't work well as well. And then we test 40 and we do see wetting. We can continue testing, get different results, and we can even try a 60 dyne solution, and wow, it looks like it is wetting. So what's happening here? Well, maybe we've put in too much dyeing solution, and that affects the reading. We always want to be able to read the center of the liquid behavior, and it's also important to understand that aside from the thermal dynamics, that there's a kinetic effect. So after we've pretreated a surface, which is time dependent, it takes some time if low molecular weight oxidized materials are going to settle. So we want to avoid dyeing pens whenever we can. The good news is that BTG Labs has invented and came out with their surface analyst, and it completely eliminates the need for dyeing pens, and this is where industry needs to go. This is a ballistic drop method in which several drops of distilled water are shot onto a surface, and virtually instantaneously you're going to be able to see what that contact angle is. And I'm not going to get into all of the details about advancing and receding contact angles, but this system does an exceptionally good job about reading the receding contact angle, which is what we're most interested, the high energy components. This is ideal for real-time production. You're not using offline equipment. Relative to Wilhelmy techniques and Cecil drop techniques that are very expensive, this is cost effective. But the most important attribute of this is that it allows for statistical process control and identifying of contamination sources. So let's move on. That beyond contact angle and surface energy, it's important to understand that you should conduct other types of surface analysis to determine what type of polar functional groups are on the surface: carbon, carbonyl, hydroperoxide, and be able to very accurately see what's going on beyond just the surface angle. Let's talk about plasmas, plasma pathways, surface pretreatments, aging, and shelf life. So what is a plasma? Plasmas can be conceptualized as a fourth state of matter. As energy is supplied, solids melt into liquids, liquids vaporize into gases, and gases ionize into plasmas, which is an extremely reactive gas. Let's now look at what happens during a plasma, and when we talk about plasmas for surface pretreatments, I'm actually going to be using a more accurate term of glow discharge plasma. So how do these plasmas actually work? The basic chemical and physical reaction that occurs in the plasma source of the pretreatment is free electrons, ions, metastables, radicals, and UV generated in the plasma impact the surface with energy sufficient to break the molecular bonds on the surface. This creates very reactive free radicals on the polymer surface that, in turn, can form, cross-link, or in the presence of oxygen, react rapidly to form various chemical functional groups on the surface. And these groups are typically identified as carbonyl, carboxyl, hydroperoxide, and hydroxyl. And even small amounts of reactive functional groups incorporated are highly beneficial to improving the surface chemical functionality as well as wettability. So we're going to examine each of the gas phase plasma modification techniques. And in the science of physics, the mechanisms in which these plasmas are generated are different, but their effects on surface wettability are similar. There's a lot of misinformation, myths, and confusing terminology in the marketplace, so I'm going to debunk all of these myths and provide you with pure scientific facts. First, on the far left, we're going to proceed to the right. This is a general overview, and on the next page, we'll go into more detail. Classical electrical corona discharge, also sometimes referred to as dielectric barrier discharge. Atmospheric plasma, sometimes referred to as electrical blown ion plasma. Electrical air plasma, referred to as blown air plasma, sometimes forced air plasma. Flame treatment, pyrosil, cold gas plasma, also known as low pressure cold gas plasma, and UV radiation ozone. I want to point out all of these photos of the electrical treatments are courtesy of 3DT. And classical electrical corona discharge uses a generator and electrodes connected to a high voltage source, a counter electrode at potential zero, and a dielectric used as a barrier. A high frequency, high voltage discharge step-up transformer creating potential difference between 2 points requiring earth ground, usually at about 35 kV and 20 to 25 kilohertz. Classical corona discharge is a very good surface cleaning process. Ozone is produced. Next, on electrical air plasma, it's a corona discharge spot treatment. In this method, the head consists of two hook electrodes in close proximity to each other connected to a high voltage transformer generating an electric arc of approximately 7 to 12 kV, but at lower frequency, 50 to 60 cycles. Then, using forced air, a continuous electrode arc produces a corona discharge or plasma. No positive ground is needed. In this process, virtually no cleaning capabilities are performed and ozone is produced. With atmospheric plasma, that utilizes a narrow nozzle or circulating rotating electrode powered by an electrical generator and step-up transformer and air. This pretreatment process can clean dirt, debris, hydrocarbons from the substrate and is excellent for that purpose. Additionally, it can create fine etching for mechanical bonding. Ozone formation is negligible. And remember, there's no such thing as zero potential or potential free that a salesperson may tell you. It should be referred to as near zero potential. Flame plasma treatment uses highly reactive species in the combustion of air and hydrocarbon. While flame treatment is exothermic, heat has actually nothing to do with the chemical functionality and the improved surface wetting. Flaming will clean dirt, debris, and hydrocarbons from the substrate. I've identified several very important parts in the center section of the slide. Most often when I'm visiting clients, I see that the flame is not properly set up. The true flame parameters actually consist of an oxidizing zone highlighted in yellow, a reducing zone or pre-combustion, which is actually unburnt gas and has nothing to do with the actual oxidation process. And then when you extend farther out, you get into the post-combustion zone, which really has negligible pretreatment effects. So to properly use the flame treatment, it's absolutely critical to have each of these zones properly set up. And I can't stress enough that before you buy any equipment, make sure that it has a zero gas pressure regulator, and also at least analyze whether or not you're using ribbon burners or drilled port. Sabrine has found that ribbon burners oftentimes provide the best result. A close cousin to flame treating is Pyrosil. And with the Pyrosil, what we actually have is that a silicone dioxide, a silicone film is actually deposited as an amorphous layer on the treated substrate. So the surface is treated with the oxidizing part of the flame, which contains a proprietary precursor, which is an organosilicone compound. And this actually forms at a thickness of about 20 to 40 nanometers silicone dioxide. And by having that intermediary layer can significantly improve adhesion bonding. And of course, most people are familiar with cold gas plasma treatment. Typically 100% oxygen is used, as well as other gases, argon and so forth, and they can be mixed in whatever proportion you want. Cold gas plasma probably is the most effective process at cleaning the surface, but it also is the most expensive, and cost matters. But the more expensive the equipment is, you're probably going to find that they have the best pumps and master flow controls, which are absolutely critical to controlling the process. Often neglected is UV radiation, which produces ozone. And we've got two primary wavelengths. One is the 185 nanometer UV light, which generally decomposes oxygen molecules and synthesizes ozone, O3, while the 245 nanometer UV decomposes ozone and produces high energy oxygen, which certainly helps to functionalize the surface. The surface will be cleaned from many organic contaminants and becomes hydrophilic. Let's advance to the shelf life. Well, I think we all know that treated polymers do have a shelf life. It can range anywhere from a few minutes for PTFE, or it can have a shelf life of over a year, and that's definitely the case with polyphenylene sulfide. In fact, the shelf life is over 1 year, and that can make a big difference because companies that want to pre-treat at the beginning of their operations have the ability to do so. Earlier in the presentation, I talked about not using polybags, and the best material we found for storing is referred to K-Pack bags, and they're polyester. I hope you're familiar with those, and they're generally available on the internet. One quick item about solvent cleaning, and obviously this presentation is not going into detail on this, but whether you're using an aliphatic solvent, ethanol, heptane, benzene, regardless of that, make sure that when you apply the solvent, it's not too heavy, or you're going to form a weak boundary layer. Wipe it clean and then plasma treat. Remember that treated surfaces are not thermodynamically stable, and the treatment can easily be rubbed off. So never plasma pre-treat and then try to wipe a surface clean. So let's see how we go about selecting a pretreatment method. Well, we always need to consider upstream and downstream manufacturing processes, such as heat sealing, and if that's the case, such as two-paste tubes, we may want to have to selectively treat. We want to know what our shelf life, desired shelf life. All equipment is not manufactured equally. Don't buy into salesmanship. Shelf life is going to make a difference. The type of polymers and colorants. Remember that carbon black can be conductive and that there are critical threshold levels. The part geometry will affect which pretreatment method, and in some cases, in addition to the part geometry, components may have metal hardware. So that would make a difference on classical corona discharge, but it would not make a difference on atmospheric. Also, we want to look into whether our mechanical automation, how well we're actually automating. So let's look at a few case studies on how Sabrine on applications perfected 0 failures on our applications.
We may want to keep these down a little bit because of time.
Yes, thank you, Jeff.
Thank you.
In the first case, this is technology that's used in all jet fighters, and that what we're trying to do is adhere the hatch explosive charge to the canopy. In this case, we used a silicone RTV to rubber, and then this is bonded to polycarbonate, and we use classical corona discharge. The next method for ice cube evaporator plates, we wanted the water to uniformly wet through the surface, and each of the ice cube machines drop the associated number of pounds of ice, and in this case, we used flame treatment. I'm going to just briefly skip to the end, near the end of our process, and I apologize for this. You'll see this on the slide, but I did want to begin to conclude and talk about that if the information that we discussed in the presentation you would like to learn more, that when Sabrine can visit your factory, we will bring with us 3 or 4 or 5 different pretreatments on your site, and we can examine each of your processes from molding through assembly. We'll bring contact angle instrumentation, temperature profiling, ASTM testing methods, and all of this can be done at your site with the exact processes that you used. So in summary, design for manufacturing. And recall, surface energy does not equal adhesion. Polymer properties matter. Always be cognizant of parts storage. Pretreatments are not only for low surface energy applications, but for other applications, they widen the process window. Avoid undertreatment and overtreatment. Use contact angle instrumentation whenever possible, not dyeing solutions. All equipment is not created equal. I want to thank all of you for your time. I hope you stay well during these difficult times. And Jeff, if we'd like to field questions.
Yeah, I think we have a couple minutes that we can do a couple questions for sure. Here's one here that asks, what effect on bond strength does boiling nylon 6,6 to increase its toughness?
Would that be before molding or after molding?
Yeah.
They can. Jeff, why don't we address that offline? I
can provide you the gentleman that asked that question. If that's good, yeah. And you guys, if you and Alan can talk later. Another question is, how does texture impact the accuracy of the surface energy measurement?
Yes, it has a considerable effect when trying to use dyeing pens or dyeing solutions because the center of the liquid behavior becomes more difficult to read. That's why you want to use the contact angle meter, Surface Analyst by BTG. It does not affect that at all.
Okay, and this here is, you've mentioned the need to have energy levels being 8 to 10 dynes higher than surface tension for a good wetting. Could you please explain why it doesn't happen to wet surface even when the difference is 20 to 30 dynes? Solid example, solid measurement. Where was it? I'm sorry. Solid measures at 40, 50 dynes, and liquid is at 30. What could be the reason?
I'm not sure from the way you're reading the question. I'd be happy to speak with the caller specifically about that.
Yes, I will definitely do that. Let's see if there's another one here we can get to real quick. Is there a foolproof process which allows adhesion of paint or ink to chrome surfaces? Typically, I've heard that you need to paint within hours of chrome plating.
Well, that's a multi-faceted question, and we really didn't talk extensively today about metals, more on plastics, but with chrome painting and so forth, there's a lot of chemical precursors that may be needed for that. So I'll go into the details with the caller directly.
Let's see. You mentioned the type of loading of C black, more specific on type and loading levels.
Yes, the loading level and the actual type of carbon black is critical. So there are furnace blacks as well as several other categories of carbon black that may or may not be conductive. And I've actually written some papers on that I could send to the caller.
Great. For pressure-sensitive adhesive surface adhesion, should there be any difference in surface adhesion between PET and HDPE?
Yes, there will be differences, but part of this will have to do with your selection of your pressure-sensitive adhesive.
And how do you correlate dyne value to contact angle values?
Great question. When one does that, and BTG as well as Sabrain has some charts for that, it must be calculated specifically for each polymer. And I'd be happy to send the caller a couple of representative charts and talk to them. But it's a straightforward process, and again, this is where the surface analyst comes very valuable.
Excellent. We're right at about an hour, so I think we're going to have to call it good there. Thank you, Scott, so much. I want to let everybody know, and they can share with their colleagues, that this will be on our website, plasticsdecorating.com, and will be up very soon under the webinar link on the navigation bar. So you can go to this and watch it again, or send a link, or let people know that they will be able to watch us. It'll be on there for quite a while. Again, thank you to SPE Decorating Assembly Division and to Plastics Decorating Magazine for the sponsor of this, and for Scott and the Sabrine Group for putting this on. Thank you, Scott, very much.
Thank you.